So we've done conservation of mass and conservation of momentum, so it's time to do conservation of energy. And this is what we did in thermo when we had, the delta H's and all that. We're going to do the same thing in fluids, only it's going to be in a different form. And just like what I did with the conservation of momentum, I'm going to start with a simple example using the equations, and then we'll go back and figure out where those equations come from. So conservation of mass you want to use if you need to find a velocity or an area, or sometimes to help you with your conservation of momentum or other equations. Conservation of momentum was about forces. This equation, conservation of energy, we're going to use that a lot, and we're going to use it for pressures, for velocities, heights, also to find work from pumps or turbines, and frictional head losses. So all kinds of things. We'll be using this equation a lot, especially when we get to chapter 6, which is internal flow. So let's get started. This equation up here is a simplified version of conservation of energy, and it's put in what's called head form, head being like a height. So all of these terms are going to be in length scales, so like feet or meters, that kind of thing. So you know what P and V and Z are. Z is height. We're always going to make Z our up and down direction. HS is our shaft work, so that means our pumps and our turbines. And you see W dot S in there, that's our power from our pump or our turbine. HF is frictional head loss. Okay, so that's what happens as you go through a pipe. Due to friction, you have some losses. Okay, so let's see how we use this equation. The main idea behind this, or the thing that makes this the easiest to use, is to draw your control volume in the best way possible. So what you want to do is look at your picture or figure out what's going on in your problem, and look at where you know velocities, where you know pressure, that kind of thing, and always surround any pumps or turbines you want to use or find out about. So in this case, we've got a pump drawing water from a big tank. We're given the total frictional head loss, that's that HF in the equation. So it says the flow discharges through a nozzle to the atmosphere. Estimate the pump power in kilowatts delivered to the water. Okay, so we have a 1, that's going to be our inlet, and a 2, it's going to be our exit. We have to make sure that we always do our 1s and 2s in the right place, where 1 is upstream from the exit. So first thing, I look here and I see, oh, here's an exit and it's atmosphere. Okay, that's a good thing. That's a good place to put something. P atmosphere, right there, because I know what P is at that point. The other thing that I see when I look at this problem is a free surface. And a free surface is another good place to put an inlet or exit. Okay, and the great thing about a free surface is usually you can, if it's a big reservoir, velocity is not going to be high. In fact, we're going to call it 0. So if I say this is my inlet way up here, not down here, but way up here, I can say this is my inlet, and I know that V1 then is going to equal 0. I also know that I can use gauge pressure just like in all my other control volume problems. So P1 is also 0. Yay, we like the zeros. Okay, so what I don't want to do is draw this through this pipe or down in this pipe. A lot of people will try to put their inlet like down at the bottom of this pipe, and you think you know the pressure there because you could say, oh, rho GH, and you know the 6 meters, and you know it's water. But that's not really the pressure there because the velocity is not 0. It's not a statics problem, so don't do it. Take your free surface as your inlet. Almost always you want to do that. So we'll put 1 as our inlet, as our free surface, and then we'll just draw our control volume like all the way out here, where it doesn't even touch any of the other stuff. It does include, in between 1 and 2, a pump and some piping. Okay, so we will have HS and we will have HF. HS for the pump and HF for the frictional head losses. Another thing we need is Z. Z is the elevation. So we just need to draw our Z coordinate on here. And I would recommend starting it at 1 or 2, doesn't really matter. I started it here at 1 at the inlet, and so I can call that 0, and then Z2 will just be 2 meters. So Z1 equals 0. Zeros are good. We want zeros. Okay, so let's go ahead and use this equation. So basically it's just draw your control volume. That's really key. Label your inlets and exits. Put your, oops, sorry about that. Put your coordinate system on there. And then start using your equation. So your equation here, oh, by the way, P2 also is at atmospheric. So that's 0 as well. Okay. So our energy equation here, after we've simplified it down to this head form, P1 over rho g plus V1 squared over 2g plus Z1 equals P2 over rho g plus V2 squared over 2g plus Z2 plus HF plus HS. All right. P1 we said was 0, P2 is 0, V1 is 0, Z1 is 0. V2 is not 0, okay? It's coming out into the air, a little jet there. Z2 we know is 2 meters, HF we're given as 5 meters, and HS, well, HS we're trying to estimate the pump power in kilowatts, so that has to do with that HS, so that's what we're going to try to find. So just rewriting this, 0 equals V2 squared over 2G plus Z2 plus HS plus HF. All right. All right. So we're trying to solve for our work of our pump, or our power from our pump. So what we want is HS. And that's going to be minus V2 squared over 2G minus Z2 minus HF. Okay, we have Z2, we have HF, we need V2. V2, did I assume average velocity? I didn't, but let's do it. Average V, okay. V2 is Q over A2, and we're given a diameter up there, D2. So if I just plug those in, 31.12 meters per second. Again, if I went through all these steps, I'd have to be very careful with units, as you should. Okay, if I plug this in now, it's just a matter of plug and chug. HS equals minus 56.4 meters. And again, you see, it should end up in a length, like feet or meters. It's negative because it's work in. Pump's always going to be negative. Okay, just like in thermo. So our HS, again, that was defined as W dot S for shaft work, so that's your pump or turbine work, over M dot G. Okay, and therefore, just rearranging, W dot S equals M dot G HS. And that equals, well, our M dot is rho Q, and then we got GHS. And rho times G is gamma, so gamma QHS. Okay, and if I just plug those numbers in, those are all things that are given, we're going to get W dot S equals minus 33.7 kilowatts. Should be watts, because this is power. The dot over it, it's power. And that power is what we need to overcome our 2 meters of elevation change and 5 meters of frictional head losses. So this overcomes 2 meters of delta Z plus 5 meters of frictional losses. And gives you kinetic energy for V2 equal 31 meters per second. That's our kinetic energy. All right, so stop and do quiz questions 1 and 2, and I'll be back.